Hello everyone. In this video, we are going to talk about one of the most, or probably the most powerful optimization command in optimization toolbox in MATLAB, fmincon, which is minimizing a cost function that is subjected to all sorts of constraints. So that con means constraint. And the good thing about this command is it is not limited to any type of specific constraint. You can literally handle any kind of constraint that you can imagine. For instance, your constraint could be linear constraint. So if x is your variable that you need to find, then the linear constraints are like a equivalent or equal, in this case, equal times x equals b equal. So this is a vector, this is a coefficient matrix. You can have inequalities that are linear. Their form is ax less than or equal b. Again, a is the coefficient matrix, b is the right-hand side, but this time it's a linear inequality, right? And the condition for it is less than or equal. And then for equalities and inequalities, we can have nonlinear functions too. For instance, you have a function called c equal of, that is a nonlinear function of this parameters in x, the variables in vector x equals 0. So for instance, it could be like, let's say x has two components, x1 and x2. It could be like x1, x2 equals, for instance, 5, right? Let's say if they are the width and height of a rectangle, this is like the area of it should be equal to 5. Well, here you bring the 5 to the other side and write it as x1, x2 minus 5 equals 0. And so this one here is basically your c equal function of x1 and x2, right? Which is equal to 0. So this is the function that you need to provide. And then sometimes we have the nonlinear inequality. Like this is the hardest one, huh? So not only it's nonlinear, it's also inequality, right? So it's like, for instance, x1, x2 squared should be less than or equal, I don't know, 8 or something, huh? So again, you bring this 8 to the other side and you make it to be minus 8 less than or equal 0. So this is going to be the c function of x1 and x2, which is the nonlinear function. Correct? So you see that you have literally all sorts of constraint here. And on the top of all of these inequalities and equalities that are linear or nonlinear, your parameters can also be within some lower bounds and upper bounds. So you have hard limits, hard thresholds on your parameters too, so upper and lower bounds. So this function can literally handle all of them together. Okay, that's why I say this is the most powerful command in optimization in MATLAB. Now, we are going to look at an example in engineering, which you see how to use this function. And then I'm going to briefly tell you about the different algorithms that this method can use. Now, the explanation for each one of them needs its own, at least one video of its own. So if I want to talk about KKT or this SQP, definitely you need one single video, at least a long video to talk about them, especially the KKT, okay? So here I want to show you how to use it for a real problem. So let's say your problem is this. You have a cantilever beam that has a load, in this case shown by P at the end. The length of the member is L. And this L is given to you as well as P. Both of them are given. So length is 2 meters. Load is 1,000 Newton. The material is like kind of like steel. So it has 210 gigapascal Young modulus and 7,800 kilogram per meter cube density. So these two are roughly a steel. And then the bending moment, of course, at the end is going to be M equal P times L. Then the allowable bending stress in the steel is 250 times 10 to the 6, or 250 megapascal. And this is like a yield strength for the steel again. Also, the end of it, when it comes down and it bends like this end point that comes down, the deformation of that delta is not supposed to exceed 5 times 10 to the negative 3, or 5 mil. So the end of it should not go down more than 5 mil. The stress in the part, the maximum stress, which happens here at this end point where this M is maximum, right? This is M maximum, and that means you have a sigma maximum, which is going to be this M maximum times half of the height of the cross section divided by I, right? So if I move a little bit to this side, it's going to be Y max divided by I, and we're going to talk about those. That should also be less than or equal this 250 megapascal. Also, we want to enforce an aspect ratio between the cross section. So this beam has a cross section, and the cross section is rectangular. And here, the two parameters for it, we call them H and B. So B is the width of the beam, H is the height of the beam. And we want the ratio between B and H to be what? The constant aspect ratio. Now, in this case, that aspect ratio is 2. That means the height is 2 times the width. So the cross section is basically more kind of vertical. So the cross section is like this. This is H, this is B, and it says H has to be 2 times B. So we want to keep a fixed aspect ratio. Also, because of the space that we have, B can only be between 10 mils and 200 mils, and H should be between 10 mils and 200 mils as well. And the envelope of it, which kind of limits the perimeter of it, says that B plus H should not be more than basically 0.2 meters or 200 mil. So B plus H is less than that, or in other words, the perimeter of that, which is 2 times this, should be less than 0.4. So there is a limit on the perimeter as well. So you see there are lots of constraints. These are all constraints, as you can see. And some of them are linear, some of them are nonlinear, equality, inequality. We're going to see them. The parameters that you need to choose are the B and H, the size of the cross section. The material is already chosen. The length, the load, they are already chosen. And the goal is to find the optimum B and H in this case. And again, remember that what we have here is a highly nonlinear problem. Now you might say, okay, what is it that you try to minimize in this case, or maximize, right? What is your cost function actually? And in this case, the function that you are trying to minimize is the mass of it. So let me show you that here. So it is shown here. You can see that it says objective is to minimize the mass of the beam. And mass is, of course, the density times the volume. And in this case, since it's a cube, it's LBH. So this is the volume, that's density. So we want to minimize this nonlinear function, of course, because it's the product of the two parameters, okay? So this is the function to be minimized. And B and H are subjected to tons of constraints. Now here, let's talk about this constraint, see how to define this constraint, and then we're going to see how to do it in MATLAB. So if we're going to go one by one, first we look at the allowable stress. Remember that the stress comes from this formula that I just showed you above. right? So it is basically PL, which is M max, and then you multiply it by Y max, which in this case is half of H, and divided by second moment of the surface, which is about the axis passing through the neutral axis. This axis, if you call it Z, for instance, that's IZZ. And then in this case, that is BH cubed over 12. Okay, so this one is H over 2. And as I said, this one is BH cubed over what? Over 12. So if I plug them in, I'm going to find a function for the stress. And you can see that over here. And this function, 6m, and remember m is a fixed number. This is p times l, and p and l are numbers. So the 6m over bh cubed, that should be less than sigma allowed. And if I bring this to the other side, now look, what you get is basically a nonlinear inequality, right? You see that the function of b and h, and the sigma allowed is a number, is less than or equal what? 0. So this is what? This is c of b and h less than or equal 0. So this is a nonlinear what? Inequality. That's for allowable stress. And typically this allowable stress, as you know, this comes from the strength of the material, right? And divided by a safety factor. And here you can see that that number is just given to us, right? So if we had the yield strength of the material, typically this is the yield strength divided by a safety factor. And by the way, you know, here I'm neglecting the effect of the mass of the beam itself on the stress and the shear force at the beam. So I'm using a very, very simple formula for sigma max. In reality, sigma max needs to come from principal stresses, and it's quite a bit more complicated than this. So here, this is assuming that basically the only thing that creates stress is due to bending, and no shear stress and no effect from the mass. So here I'm gonna just add that for you here. Good. So that's your first constraint. What else? The next thing is the deflection at the tip should be no more than 5 mil. Remember the second one? And deflection of the beam from solid mechanics is also a function of the parameters of the beam. So it's PL cubed over 3EI, where I, if you remember, I is this guy here, BH cubed over 12, right? And so PL cubed over 3EI, where I, again, is a function of B and H. This guy should be less than sigma allowed. Again, you bring it to the other side. It's less than or equal 0. So you see, this is your second function that is a nonlinear inequality, right? You see, again, B and H are in the I, and sigma allowed is 5 mil. So this is what? Your second nonlinear inequality. So if that one was C1, this one is what? C2 of B and H is less than or equal 0. So two of them here. You might even want to add something like the minimum frequency is so much, right? So we can look at the vibrations as well. And from vibrations, you calculate the frequency, the natural frequency of a cantilever beam, and set a limit on that. That's another nonlinear inequality if you want. Okay, what else do we have? The one that you said that the aspect ratio should be 2, in other words, H is 2 times B, or H minus 2B equals 0. This one, this aspect ratio one, is a linear, as you can see, equality. So it's a linear function of H and B, and it's equal to something. So that's the easiest one to consider. And the one that has a limit on the perimeter, or the working envelope, this last one, basically, this is, again, linear because B and H are linear functions, but it's an inequality because it's less than 0.2, so you have a linear inequality in this case. Okay? So now with all of that in mind, we are going to what? We are going to basically solve this problem. So we have all of these constraints plus your H and B, they have hard constraint. They have upper and lower bound, and they are what? They are provided to us. Each one of them could be between basically 10 mil to 200 mil. So this should also be considered when we are basically minimizing this function. Okay, now that we have all of them, how do we code it in MATLAB? Let's take a look at this function. Now, as I said, the command to use is fmincon. And if you look at the syntax of fmincon in MATLAB, you are going to see how this function is used. So if we go to the help page for it, you can see that this function, this is the most general line, this line 5. You pass to it the function, you pass to it the initial guess, A and B for linear inequality, EQ and B EQ. This is for linear equality. Lower bound and upper bound are the vectors of lower and upper on the parameters. Nonlinear constraint. This one could be nonlinear, either equality or inequality or both. So this one, any nonlinear thing that you have, any nonlinear constraint, whether equality or inequality, is provided inside this function. And then the solutions and options for the solution and the methods, the algorithm. So that you can do with optim set, right? So let's go here. You can see in this code that I'm going to share with you, all of these parameters that we know are provided, including the load, the density, the Young modulus, the length, the allowable sigma, the allowable delta, the given aspect ratio, the upper and the lower bound. And look here, the lower bound for both parameters are provided in one vector, and the upper bound for both of them, again, provided in one vector. And you see they are column vectors. Then, for the equation B plus H less than equal 0.2, your linear inequality is of which form? It's of this form. If you can see it, AX is less than B. Okay, and in your case, this is the equation. B plus H is less than 0.2. So this 0.2 is your B, and you have to write the left-hand side, which is B plus H. You have to write it as a matrix times vector X. And vector X in this case is the vector of the unknowns, which is B and H. So the only way to write it is a 1, 1 times B and H is less than what? 0.2. So you see this is your A, and this is what? This is your B. So that's how you got these vectors in the MATLAB code. Similarly, for aspect ratio, remember the equation is H minus KB equals 0. So the coefficient matrix is, because B is our first parameter, you can also write it like this if you want. Negative KB plus H equals 0. And that means the coefficient of B is negative K, the coefficient of H is 1, and the right-hand side is 0, so B of equal is 0, and A of it is negative K and 1. So there we go. The linear ones are defined, the bounds are defined. The initial guess here, we use 0.03 and K times 0.03, which is 0.06. So here we, by this initial guess, we try to make sure that the initial guess matches the linear equality. So we set it such that it already satisfies this one. You don't have to do that. If you want, you can change it and give it a different number. And here you can see that it tries to make sure that your initial guess is as close as possible to satisfy one of the constraints. Now, your cost function to minimize, as you can see, is rho times L times x1 and x2, which are B and H. So that's your volume, that's your density, so it's the mass. And look at your nonlinear. So this is the important part. Your nonlinear function, which here we called L-con and then simple. Now this is just a name. Call it whatever you like. It's just a name. There is no requirement on that. This one not only will return the nonlinear inequalities, it also will return what? The linear equalities, okay? So here, that single function is going to return both of these for you, both C equal and C. So let's go ahead and take a look. What would you give it? You give it X, you give it these parameters that you need, MPLE, delta allowed, sigma allowed, and it defines B and H as X1 and X2. First, make sure that B and H are not negative, because in this case they are dimensions. And then it defines the moment of inertia. It defines the first nonlinear inequality, and then the second nonlinear inequality. This is for the stress, this is for deflection. And then since you have two of them, you're going to merge them into one single C. So the C has C1 and C2 functions in it. Now, in this case, there is no nonlinear equality between B and H. So you leave it as what? You leave it as empty. If there was anything, you have to define it here. But since there is none, you just call it empty. The same goes for anything else. Let's say you don't have a linear equality, right? If there is no linear equality, then make sure this A equal and B equal, they are empty brackets, right? Or if there is no lower bound and upper bound, again, empty bracket. If there is no linear inequality, make A and B linear to be what? To be basically empty bracket. So whatever you don't have, leave it as empty bracket. Now, look what we do here. The options for the fmincon are, first we say that the function I want you to use to minimize this problem is fmincon, of course, if we have to. The algorithm is SQP. I want you to show the iterations of the solution, as we'll see. I want you to plot several results for me. Okay, so here we are asking it to give us three types of plot, right? Optim plot X, optim plot fval, and optim plot constr or constraint violation. So it plots for you the X values final, it plots for you the F value, and it will plot for you the final violation of the constraints, right? Because the constraints should not be violated, but here it tries to enforce them as much as it can. So the closer this number is to 0, that means the constraints are almost close to perfect applied. Just use 200 iterations max, and then maximum function evaluations is 5,000, constraint tolerance, and optimality constraint. Now, before I show you how to use the fmin command, I want to mention something. This method needs the gradient of the cost function, okay? This function that you're trying to minimize, and in this case, remember, that's the mass. And sometimes it also needs gradient for these nonlinear constraints, right? Because it is going to linearize everything around the operating point. And so if your function is such that whether the cost function or this constraint function is such that you know the gradient of it, you can provide it. So it doesn't need to calculate it numerically by finite difference. That makes your calculations faster and easier. So again, in this case, for instance, I want the derivative of the cost function, right? This one with respect to x1 and x2, well, I can easily calculate that, right? It's no big deal. So it's rho LH for B and rho LB for H, right? It's very easy, the partial derivatives, the gradient function. But again, sometimes you don't have it. You're just working with numbers only. You don't have a function. Fine, you allow it to do it numerically. But if you have it, it helps. Now, how do you provide that? If you do have the gradient, then this cost function fun not only must return the cost function, it should also provide the gradient as well for it. And the same thing for C and C inequality. You have to provide that. And then in the optim options, you say that, hey, specify object gradient true. says, hey, I am going to specify the gradient for you analytically, is true. By default, this is false, so it doesn't expect you to provide it. But if you say true, now you have to provide that. And so I want you to pay attention to that part. For instance, for the cost function, it should look like this. It says, hey, the objective function is at x of objective, x, r, and l, very similar. But instead of using a simple anonymous function, now for this objective, you write a function. Now, what does this function return? Instead of just returning a single number, it returns f and g, where f is the cost function, g is the gradient of it. And you see, this is the same cost function as you had up there. But now look, row LH and row LB, this is the gradient of that function with respect to the vector x. Okay, so you have to use this as opposed to simply what? That one, if you want to provide the gradient for the cost function. And here I added the next one also as comment for you. So these are the nonlinear constraints that also have gradients in them. And you see, similar to this one that I'm using, you pass all of the parameters, but instead of just giving you functions C1 and C2 and no equality, right? What does this one say? First of all, you see that it calculates everything. It calculates C1 and C2. And so this first part of it is exactly similar to the part above. Now, look, here it calculates the gradients for you. And that's the gradient of C1 for B. That's the gradient of C1 for H. And then C2 for B and C2 for H. Okay? And then here, we are putting the gradient of C1 with respect to B and H in the first column and C2 for B and H in the second column. And for C equal, it doesn't exist, so the gradient of that also doesn't exist. You see that? Yeah? So clearly here, you see that this function not only return for you C and C equal, it also returns the gradient of C and the gradient of the C equal. And you have to write this big of a function for it so it can be used. Okay, so if you want, you can go ahead and let me add something here. So I say uncomment this part to provide the gradients for the constraints. Right? And similarly here, I'm going to do a similar thing for the cost function, right here. So you uncomment this part to provide gradient for the cost function. Okay, so you can uncomment them and you can try them with the cost function if you want. But if you don't, the one that you have already is going to work, and I provided this extra explanation here, so maybe this explanation also need to go all the way to the top here, right? Maybe right here. Okay, so providing the gradients or instructions for. Good. So now that we have all of them set and we have the upper and lower bound, look, I passed the cost function, I passed the initial guess, I passed the linearity, the linear inequality, the linear equality, the lower and upper bound, the nonlinear functions for both equality and inequality, and all of the options. It gives me back the optimum value, the value of the function at the optimum, exit flag, and an output function if you have one. Okay, and then once I get the results, then I'm gonna call them H optimum and B optimum. I get the mass optimum, the I, sigma, everything, and I can do some post-processing and show the final results on the screen. Okay, now that we have everything, it is time to what? It is time to run it, see what happens. So let's go ahead and run. And this is the plot part that we activated. And you see that actually very fast it converged. The reason is we have too many constraints. And the one that makes life very easy is that equality constraint, because now you're really doing a 1D function, because one of them is a linear function of the other one. So basically it easily converts it to a 1D problem. But if this guy was not there, the problem would not be that easy to converge. So here you see that in about 6 iterations, 7 iterations, it reached to the best it could. And it says that, hey, it's not decreasing anymore. So this is the best that I could get. Of course, with the optimality tolerance and the constraint tolerance. And if we go down here, it shows you that like 44 mil for B and 88 mil for H is the best set. The best mass you can get is 60 kilogram. This is the moment and the cross section if you want. Then the maximum bending stress, it is going to be, as you can see, much less than the allowable. The tip deflection is basically almost at the allowable number. Then it took 6 iterations, the algorithm, everything, and you see that the constraint violation is extremely small. And that is what you can see also toward the very end, that when you are at 6 iteration now, your constraint violation is too small that it is good. And this is the value of the function mass here, 60. And here, these are the values of the final values for B and H. Okay, so they changed over a range and they ended up at this mid numbers here that you can see, 0.44 and 0.88. Now, if I go ahead and get rid of this basically constraints, the linear equality constraint that make the problem very simple, what's going to happen here? So here, I'm going to comment these out and I'm going to make these empty brackets, right? So we don't have them. Now let's see what happens. Okay, still not bad. Took 7 iterations. And if you look at the numbers, this time the numbers are quite a bit different than last time, because the aspect ratio of 1 to 2 is not enforced. But look, because you didn't enforce it, now you can get the beam mass of the beam down to 22 kilogram as opposed to what? 60 kilograms. So that constraint is really changing everything. And now you can see that, again, everything is good. And then let's say, for instance, I get rid of this linear inequality as well, that the perimeter should be less than so much. Let's get rid of that as well, see what happens. So the only things we are going to apply are the maximum stress and the maximum deflection at the tip of the beam. So let's see what happens. Okay, seems like again it converges in 7 iterations. That's very interesting. And results is almost the same as before. So that did not do much of a change, because apparently the solution that it was found last time already satisfied this linear basically inequality. Okay, so this one did not really do much of a change. But clearly, by adding more constraint, the solution has a very limited region to move, so you might not get some very, very small mass because you have a very small region for the parameters to move within. I'm going to share this code with you under the video description, and hopefully you learned that how this fmincon command can be applied in MATLAB to an engineering problem. Now, before I finish this video, I want to just mention briefly what I promised you, and that is, what are the algorithms for this command? As I said, there are 4 major algorithms. One of them is called SQP, or sequential quadratic programming. This one alone needs at least 1 video or more just to explain it. Okay, but if you want to use this, where should you use it? This is good for when the problems are smooth and reliable and robust. In this case, the function was very smooth. It's just all of these B, H, L, and rho multiplied, okay? And none of these functions that you see, the constraint, anything was a piecewise continuous or anything. They were all nice, smooth functions. So SQP is very good for that. There is another one called interior point. This is based on the KKT method. And again, KKT, the Karushkan, this is a complicated thing. It needs 1 or 2 lectures just to explain how this guy works. But this is good when the problems are large. You have a ton of variables and the space could also be sparse. There is another one called active set. And this is good if your problems are smart or when you expect the boundaries to be active, which means the boundaries to change over time, not be fixed. Very interesting, huh? And finally, we have what we call truss region reflective. This is only for the problems where the bounds and the constraints are all linear. So there should be no nonlinearity in your constraint, whether equality or inequality. If they are all equal, you can use this truss region Newton method and it can solve it pretty efficient for you. Okay, so now you see that each one of these algorithms for this fmincon is based on what kind of problem that you are trying to solve. Again, each one of them needs 1 or 2 videos just to explain them. So I try to avoid it here and just provide you the overall knowledge. Thank you for your attention. Hopefully the video was useful and I'll see you in the next video.